hammer an iron nail, you apply force on the flat side of the nail. The pointed side of the nail, which is in contact with the wall, then applies the force on the wall and tries to pierce it. Now let me ask you an interesting question. What will happen if you hammer the pointed side and try to pierce the flat side of the nail? You will find it difficult to push the flat face of the nail through the wall even if you apply more force than you did in the first case. What is the reason for this? The reason is that the pressure applied by the tip of the nail on the wall is more than the pressure applied by the nail's flat surface. But the question is why? First, notice that the area of the tip of the nail is very less as compared to the area of its flat surface. This tells us that the area of the surface on which the force is applied matters. We will understand this in detail, but first let us define pressure. We define pressure as the perpendicular force acting on the surface of an object per unit area on which it's acting. It's easy. Force acting per unit area. We already know that the SI unit of force is Newton, denoted by N, and that of the area is meter squared. So the SI unit of pressure is Newton per meter squared. It is also called Pascal, which is denoted by PA. Why is it called Pascal? It is given this name to honor the achievements of a French scientist named Blaise Pascal for his contributions in hydrostatics and hydrodynamics. Observe the equation carefully. Area is in the denominator of the fraction. What is this area? Well, this area is nothing but the area on which force is applied. Say I keep the force constant and I keep increasing this area. What will happen to the pressure? Will the pressure increase or decrease? Use pure mathematical logic to answer this. If I have a fraction and I keep the term in the numerator constant and keep increasing the term in the denominator, then will the fraction increase or decrease? Surely it will decrease. So the pressure will decrease if I increase the area while keeping the force constant. With this newfound knowledge, let's go back to the example we saw earlier, the nail and the wall. Notice that we are also applying the force perpendicular to the surface of the wall. The angle between the nail and the wall is 90 degrees and not anything else. If you notice, the tip of the nail has a very small area compared to the flat surface of the nail, and hence the area of contact with the wall reduces to great extent in the first case. Hence, the pressure applied by the tip on the wall is greater than the pressure applied by the flat surface. That is why it is easy for the tip of the nail to penetrate through the wall. You can even use drill machines to drill the hole into the wall. You see that it has the pointed tip for the same reason. You can easily cut the vegetables using the cutting edge of the knife. But if you use the blunt edge of the knife, it will be difficult to penetrate it in. What is the reason in this case? Well, in the first sight, the two edges might look the same to us. But if you look at them carefully, the cutting edge has small triangle-like shapes with sharp outer points. The other edge has nothing of these. So if you cut a vegetable with a cutting edge, the area of contact between the vegetable and the knife is greatly reduced. Hence, more pressure is applied on the vegetables using cutting edge of the knife. Area used to cut the trees also have sharp cutting edges instead of placid ones. It increases the pressure on the tree due to the less area of contact. The examples that we've seen so far are applications of high pressure. It's about how high pressure is useful to us in some cases. But it is not always the case. There are situations where we require low pressure. Let us see some applications or advantages of low pressure. We use snowshoes to walk on snow. The reason for that is simple. Due to the larger area in contact with the snow, snowshoes reduces the pressure on the snow. We are able to walk on it without our feet sinking deep inside. In case of normal shoes, due to comparatively smaller area of contact, the pressure on snow is more and it sinks our feet deep inside. Note that the force applied on the snow in both the cases is the same. This force is nothing but our weight on the snow. Have you ever wondered why the wheels of an army tank run on the steel tracks rather on the ground? Notice that the wheels are on steel tracks and are not touching the ground. The army tank is huge in size. If the wheels run on ground, due to less contact area with the ground, the pressure on the ground will be massive. However, the tracks have much larger area of contact with the ground and hence the pressure on the ground is reduced to a great extent. In all the examples that we have seen in this video, it is the solid which is applying pressure on another solid. Do liquids also apply pressure? We will see that in the next video.
Fluid. Fluid is any substance at a particular temperature and pressure which cannot take any shear stress Liquids and gases usually have this property and hence are referred to as fluids. Referred to as fluids. So this is a basic definition of fluid, which is any substance at a particular temperature. You can see here any substance at a particular temperature and pressure which cannot take any shear stress, and the examples are liquid and gases. So most of the people get confused with fluids, that they only claim it is to be a liquid, but it is a liquid and gases which is usually have the property mentioned above and hence they are referred to as fluids, right? So this chapter of fluid mechanics has three aspects. First, fluid statics. Which is nothing but the study of fluids at rest. Then comes the fluid dynamics. Study of fluids in motion. Then comes the fluid properties. Which is study of special properties of fluids. Good? Yeah. So let us try to understand this. First is fluid statics. So what is fluid statics? So in fluid statics, it is nothing but the other name of this is hydrostatics. So let us try to understand the definition in this. What is fluid pressure? So the analysis of fluid pressure is centrally important in this study of fluids, right? So let us try to understand this. What is fluid pressure? So in order to make it more clear, let me say that there is a liquid which is contained in a beaker. So let's say this is a beaker. And inside the beaker there is a water, or you can say there is a liquid. We will say there is a liquid and the density of the liquid is D. Now let us take the volume of the liquid which is at the bottom here, right? Let B be the point at the base of the imaginary liquid column. So let the point be B, which is at the base of the liquid column. And let me say this is my column. Let's say this is my point A and this is your beaker. Now the height of the column is H. Volume of the imaginary column of liquid is equal to, what is the volume? The volume is area of cross section multiplied by length, the length of the column. So what is the area of cross section? Let us say it is A, and the height, that is length, is nothing but the height, right? So now let us calculate the weight of the liquid column. So weight of the liquid column is equal to mg, which is equal to ah into d into g. Now what is mass? So density is equal to mass upon volume. So mass is equal to density, let's say density is d into volume. Volume is what? A into h. So this mass is being substituted here, which is equal to ah dg, right? Now this is the weight of the liquid column. Now pressure due to the liquid column at the base, let's say point B, is equal to F by A, which is equal to AH dg by A, which is equal to H dg, right? So this is the mathematical expression for pressure in fluids, right? Now let us try to understand the characteristics of liquid pressure. The first characteristic, pressure increases with depth of liquid. Pressure increases with the depth of liquid. liquid exerted lateral pressure, or else we can say that lateral pressure in a liquid increases with depth. Third, pressure at any point within a liquid at rest acts equally in all directions. Then pressure of a liquid depends on the density of the liquid. Then liquid pressure acts uniformly on any area when the liquid is at rest. Its free surface is horizontal. When the liquid is at rest, the upward and the downward pressure at any point within the liquids are equal.
A wooden block kept on a table exerts a force on it, and we know that the wooden block is a solid substance. What about liquids? We know that liquids are kept in containers. Do liquids or fluids exert pressure? Yes, they do. They exert pressure on the base and the walls of the container in which they are enclosed. The pressure on the base will be downwards, and on the walls the pressure will be sidewards. We can also derive something interesting if we look at the fluid in terms of layers. Say there's water kept in a plastic container. Let's divide the fluid into 5 equal parts. You can see that the second layer of water is holding the weight of the first layer. Similarly, the third layer is holding the weight of the first as well as the second layer. And the fourth layer is holding the weight of the top 3 layers, and so on and so forth. So clearly, the pressure at the bottommost layer is the maximum. There's even a way you can find this out. Near the topmost layer, make a little hole at the side. You'll see that the water flows out from that hole like this. It doesn't roll along the walls, it flows out at an angle. Now let's make a second hole near the layer under it. You'll see that the water flows out at a wider angle as compared to the earlier case. We continue to make holes in the wall, and we'll notice that the water literally squirts out. This proves that the pressure at the bottom is much more than the pressure at the topmost layer. What about the upward force exerted by a liquid? How do we understand that? We will see that in our next video. Say you're holding a slightly heavy object in your hand. Now, if you try to hold that object within a container full of water, you'll notice that it feels lighter. It doesn't feel heavy at all. What happens when you put an empty glass into a container of water? Of course, the glass fills up with water. So you're holding the glass of water inside the water which is in the container. And now, when you try to take the glass outside the water, what do you notice? Yes, the glass feels heavier when it's outside the fluid. And the same glass full of water felt light when it was placed inside the fluid. And that brings us to the concept of buoyancy. What happens when an object is placed inside a fluid? As we'd seen in the previous video, the fluid pressure increases with depth. Now, because the pressure increases as we go deeper, the force exerted upward due to the pressure will be more than the pressure exerted downwards due to the pressure. So the force exerted on the bottom of the object due to pressure will be more than the force exerted on the top. So this net upward force exerted on objects submerged in fluids is called the buoyant force. You can test this with a tightly closed empty plastic bottle and a container of water. If you drop the bottle on the fluid, you will see that it will float. That's because the fluid is applying an upward force on the bottle. Now hold the bottle and push it inside the fluid. You'd notice that the bottle is also exerting an upward force on your hand. If you leave the bottle, you'll see that the bottle will come up to the surface on its own. I think you can guess why. Now push the bottle deeper inside the fluid. You will feel more force against your hand. And when you release the bottle, it'll rush back to the surface. It'll come up faster than it came up in the previous case. The upward force increases as it's pushed deeper into the fluid. And that's because the pressure also increases as we go deeper into the fluid. This upward force exerted by the water on the bottle is known as upthrust or the buoyant force. Now let's say you simultaneously drop a piece of balsa wood and a metal drawing pin of the same mass into a container filled with water. What do you think will happen? Will both of them float? Or will they both sink? Or one stays afloat and one sinks? We will understand this example in the next video. Say you have a beaker filled with water and you put your index finger inside it. You'll observe that the water level rises slightly. You put in 2 fingers, the water level rises a bit more. And now when you put in your hand up to the wrist level, you'll see that the water level increases significantly. The ancient Greek mathematician Archimedes observed something similar when he got into a bathtub. When he got in, he realized that the level of water went up. In both the cases, you notice that the water is displaced by the object that goes in. Keep this thought in mind. We'll come back to it soon. In our previous videos, we've seen that when an object is placed in or on the fluid exerts a buoyant force on it which acts upwards. The Archimedes Principle goes just one step further in saying that the buoyant force applied by the fluid is equal to the weight of the displaced fluid. We can take a simple example to understand this. Take a 5 kg solid object and suspend it by a spring balance. The balance will read 5 kilograms. Let this be the first case. For the second case, take a beaker of water which has a small opening at the top. The water in the beaker is filled right up to this point where the opening is. And we keep a small container under the opening. Now slowly lower the solid object into the water and you'll see that the reading will be lower number as compared to the previous case. Why is that? It's because of the buoyant force acting on the object. You'd have also noticed that some water was displaced. Now in this context, we can say that the weight of this displaced water is equal to the magnitude of the buoyant force acting on the object. That's the Archimedes Principle. When an object is immersed fully or partially in a fluid, the upward force applied by the fluid on the object is the same as the weight of the fluid displaced by the object. Where is this principle applied? Can you think of examples? How do you think large steel ships float? It's simple. if the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, then everything above the keel will remain afloat. That's because the water too applies an upward buoyant force on the ship, which is same as the weight of the water displaced by it. There's just one important concept left in this section, and that's relative density, which we will cover in the next lesson. We've understood what density is. In the same given amount of space, if there are more things, we say that it's denser. Density is simply the measure of how compact the mass in a substance or object is. It's mass per unit volume. And based on this formula, we can say that its unit is kilogram per meter cubed. So can you tell me what relative density is? Look at the word relative. What does it tell you? It tells us that we are looking at the density of something relative to the density of something. We are comparing the density of one thing to the density of another. That's all. But the question is, relative to what? It's most typically the density of water. Yes, we look at the density of an object relative to the density of water. How do we define the relative density of a substance? It equals the ratio of its density to that of water. Yes, density of the substance over the density of water. Can you tell me the unit of relative density? Look at the right-hand side and tell me the unit. As it is a ratio of similar quantities, relative density will have no units. The units from the numerator and denominator cancel each other out. The density of water is 1000 kilograms per meter cubed and the density of silver is 10,500 kilograms per meter cubed. So can you tell me the relative density of silver? It's easy. Just refer to this formula and try answering it. It will equal the density of silver over the density of water. Substituting the values here, we get the answer as 10.5. That's the relative density of silver. What does the relative density tell us though? What can we understand from this? First, it tells us that silver is a lot more dense than water under the given conditions. Approximately 10.5 times denser. But that's pretty obvious given the numbers. This tells us another important thing. It tells us whether the object will float or sink in water. In simple terms, a substance will sink if it's denser than the liquid it's placed in. And it will float if it's less dense than the liquid it's placed in. How can we say this mathematically? If the relative density of a substance is greater than 1, then it will sink, and if it's lesser than 1, it will float. As the relative density of silver is 10.5, which is greater than 1, it will sink in water. But if we take the example of ice, its density is approximately 934 kilograms per meter cubed. So its relative density will be 0.934. As its relative density is lesser than 1, it will float in water. We can understand this with a simple diagram. Take 4 beakers filled with water. In the first one, drop a substance with a relative density of 0.1. You'll see that it floats like this. In the second one, drop a substance with relative density of 0.4 and you'll see that it floats like this. More of it is inside the water. And if it's 0.9, even more of it will be inside the water. But it will still float. And if it's greater than 1, say 1.2 or 1.3, then it will sink. Okay, here's one last question for you. Can the relative density of an object be 0? The answer is no, it can't be 0. Because if the relative density is 0, it will mean that the density of the substance is 0, which in turn will mean that the mass of the substance is 0. For any given substance, its mass in a given volume cannot be 0. And you should also know that relative density is constant only under given conditions. It is pressure and temperature dependent. The same substance can have different relative densities under different pressures or temperatures.